Okay, today we're going to look at slope fields. And what a slope field is it's a field of slopes, kind of like a field of corn. But instead of a stalk of corn, you have slopes at each spot. So each of these red dots, we're going to try to draw the slope. And basically the way you do it is that for each point, you have an x and a y. So this would be negative 1, 1. And you plug it into your differential equation. This says that the derivative is 2x. And that's the same thing as saying that the slope is 2x. And we're dealing with an example that only depends on x. So it doesn't matter what the y is. In this case, our x is negative 1. So we're going to plug in a negative 1 right here. And that's going to give us 2 times negative 1. So that would be negative 2. So at that spot right here, the slope is going to be negative 2. Now what does it mean to have a slope that's negative 2? Well, it means that you would go down 2 and right 1. So we want this kind of slope right here at this spot over here. So we're going to drag one of these over here. There we go. And because this is a differential equation that only depends on x, then it doesn't matter what the y value is. As long as your x is negative 1, you're going to have the same slope. So we can actually copy that slope for all three of those points. Now let's try another point, maybe 0, 0, for example. If I plug in the point 0, 0, it's the x value that's being plugged in because this slope field only depends on x. So if I plug in my 0 for the x, I'm getting 2 times 0, which is 0. And a slope of 0 looks like this. So we can drag this over here. And when x is 0, the slope is 0. And it doesn't matter what the y value is. So we can put all three of these slopes here. And the AP test will generally only give you about 9 or 12 points to do. Again, because this only depends on x, all three of these are going to have the exact same slope. All three of these will have the same slope, and all three of these will have the same slope. And that's because in each column, all 3 points have the same x value. So really, I only have to calculate one slope here, and one slope there, and then I can copy everything in that column. It will all have the same slope. So let's do the last one. That's the point 1, 0. So our x value is 1. We're getting a slope of 2. And the slope of 2 looks something like this. You go up 2 and you go right 1. Doesn't have to be perfect. You just want to estimate it the best that you can. There we go. And now we are done with our slope field. Now a real slope field has a slope at every single point. So every single one of these points should have a slope. However, the AP test is only going to ask you to do about 9 or 12 of them. So you don't have to fill out the entire slope field. Now in a later example, we are going to look at how you can draw your original function through this slope field. For this example, our function was probably y equals x squared plus a number, maybe plus 2 as an example. And so when I did the derivative, I just got 2x. Now it could have been x squared plus 1. It could have been x squared plus 0. It could have even been x squared minus 1. We do not know what the constant was because we have the derivative equals 2x. So we don't know what our plus c could have been. So if it was just x squared, it probably would have looked something like this. Again, that was just an example. Maybe it was x squared minus 1, and then it would look something like this. So hopefully you're starting to get an idea of how we're going to use the slope field later. But in this problem, we're not doing that. All we're doing is just drawing the slope field. And in this case, it's just 9 points of the entire slope field. We're not even drawing the whole thing. All right, let's go ahead and move on to another example. Our next example depends on x and y. You can see for this example, our derivative was equal to negative x over y. Now let's take a look at how we got that. The original equation was actually a circle, and we're doing the derivative with respect to x on both sides. If we do that, the derivative of x squared is just going to be 2x. The derivative of y squared is going to be 2y and then y prime. The derivative of a constant is just going to be 0. Now we do want to solve for y prime. So I'm going to start by subtracting 2x from both sides. Again, I'm trying to solve for the y prime. So I'm going to want to divide both sides by 2y now. There we go. We have solved for the y prime. You can see we can cancel the 2's here. And I'm left with y prime is equal to negative x over y. Now that's the same thing as dy dx is equal to negative x over y. So if our original function was a circle of radius r centered at the origin, then the derivative would be negative x over y. So let's go back to our example now. You might be able to see that this really is a slope field for a circle. So if the circle was a radius of 1, it might be something like this. If the circle was a radius of 2, it might be something like this. A circle with a radius of about 1.4 would be the green one. You can see how it kind of goes through all the slope field lines perfectly. But now let's back up and let's see how we got this slope field. So usually when you do these problems, you don't know what it's going to look like. So for each point, you just have to plug in the x and plug in the y and see what the slope is. We're going to do this point by point, and we're going to see what happens. Let's just start with this point right here. This is the point -1, 2. And if you plug it into our differential equation, we're going to get negative and then -1/2. You can see we have two negatives. So these negatives are going to cancel, and you're just going to get 1/2. So the slope is going to be 1/2. A slope of 1/2 means you go up 1, and then you go right 2. So the slope of 1/2 looks something like this. When you draw it, it doesn't have to be perfect. You just want to estimate it the best that you can. Now we are not going to be able to copy it for everything in this column, because this equation here depends on x and it also depends on y. So these different y values are going to give you different slopes. Let's look at this point right here. This is the point -1, 1. If we plug it into our equation, we're going to get -1/1. And again, we do have two negatives, so they're going to cancel. So we just get +1 for the slope. So the slope of +1 looks something like this. You go up 1 and right 1. So it's going to look something like this. Again, when you draw it, it doesn't have to be perfect. You just want to estimate it the best that you can. So this slope should aim for the top corner of that box right there. The previous slope was a slope of 1/2. So that would be going up 1 and right 2. So you'd be aiming for this spot right here. You just want to estimate it the best that you can. It does not need to be perfect. Now we would copy that for these other 6 points. Same thing that we did here. You plug in the x, you plug in the y. You want to copy that for those other 6 points. Now there is something weird happening when x is 0 or when y is 0. Let's first look at what happens when x is 0. For all of these points, when x is 0, you're plugging a 0 into the top. So when you plug a 0 into the top, it doesn't matter what the y is. The number itself is just going to be 0. So all 4 of these slopes are going to be 0. So that's good news. That makes it easier. We had 12 points to graph, but all 4 of these are going to be the same slope. So that saves us a little bit. You'll notice we did not plot this slope when y was 0, and that's because if y is 0, you get undefined. Now y is 0 is the x-axis. So if we let y equal 0, we get undefined, and that's the x-axis. So there are no vertical slopes on the x-axis. There are no slopes drawn over here. And the AP test isn't even going to put a point there for you to draw it, because you should never, never draw vertical tangent slopes. They do not want you to draw a vertical tangent slope. And if I was going to draw a circle here, we're going to learn in our next example that if I was going to draw a circle here, I would have to stop on the x-axis. So basically, I have to leave it as an open circle. That's how I would draw it, because you're not allowed to go through a vertical tangent line. Every point on the x-axis is going to be a vertical tangent line for this example. If I was allowed to draw the entire circle, it might look something like this, but right here and right here, we are going through a vertical tangent line, and that's not allowed. We are not allowed to draw our graph through vertical tangent lines. So if you ever get to a spot where it's a vertical tangent line, you just stop and put an open circle. And we're going to learn that in our next example. For now, all we're doing is we're just plotting the slope at each of these points that they're asking us to. And they usually put these little dots at the spots where they want you to graph the slopes. Now, if we go back and look at number 1, you see that this equation here is called a differential equation. And a differential equation just gives a relationship between a function and its derivatives. Again, this here is a differential equation, and it's giving a relationship between a function and its derivatives. We're going to look at our last example here. For our last example, we're going to draw a particular solution. So right now we're looking at the slope field for this differential equation. I think you can see that this differential equation represents a set of hyperbolas. And whenever you draw a particular solution, it must satisfy these 5 conditions here. Your particular solution must be a continuous differentiable function on a single open interval that contains the point that they give you. Now, if I was going to actually draw the entire hyperbola, it would probably look something like this. You start at your point, and then you start drawing, and you just follow the slope field lines. Anytime you touch one of these slope field lines, you just stay on the line. And if I was to copy that on the other side, it might look something like this. And that's an example of what a hyperbola might look like that goes through this point right here. Now, this would not work for a particular solution for a lot of different reasons. One of them is it has to be drawn on a single open interval. And this one is drawn on two separate intervals. So that can't happen. So what if we erase the left side of the hyperbola? Would this be acceptable? Well, we now have a check mark for that one. And the reason why I chose the right side and not the left side is because it must contain this point. So we can also put a check mark for that one. The function that we currently have is drawn on a single open interval that contains that point. The problem is that this is not a function. It does not pass the vertical line test. If I draw a vertical line, I think you can see that it's intersecting our graph more than once. So this is not a function. How about if I erase the bottom of it? There we go. Now I have a function. So I can put a check mark on that. Is this continuous? Yes, it is continuous. Is it differentiable? Well, the derivative does not exist at this point right here. If you have an endpoint, the derivative does not exist. So what we're going to have to do is we're going to have to put an open circle right here. There we go. Now we can check the last box over here. Now we do have a differentiable function. So a particular solution must check all 5 of these boxes over here. It must be a continuous differentiable function on a single open interval that contains that point. So they do give you the point. Every time they ask you to draw a particular solution, they must give you a point. Make sure you write down all 5 of those things. This is very important. And now I think it's time to go practice some examples.